Okay, good day, everyone, and welcome to our webinar on safe combustion control for hydrogen-fueled burners, which will be presented by Tim Talon. My name is John Kearney, and I lead the product management team here at AMETEK Process Instruments. And today I'll serve as the moderator for the session. We are excited to share some interesting and educational information on the use of hydrogen as a fuel, what makes the combustion a bit different than standard fuels, and how to ensure safe combustion control. Before I turn the presentation over to Tim to introduce himself and begin sharing his content, I just wanted to cover a few logistic items with everybody. We are recording the session, and just to minimize the background noise so we have a nice recording, just ask to make sure that your computer microphone, or if you're joining on your mobile phone, that your microphone is muted. We do want the session to be interactive, so there is a chat feature in Microsoft Teams that can be used. For those perhaps not familiar with the platform, in the top right portion of your screen, there is an icon there that looks like a quotation mark. If you click on that, the chat box will appear on the right-hand side of the screen, and you can type your chat into the chat your question, and I'll try to have Tim address those at the end of the presentation. As I mentioned, this webinar is being recorded, and we will share the recording within a day or so on our AMETEK Process Instruments YouTube page. I did include a link to that YouTube page in the chat, and I'll put that in as well at the end of the session. This webinar is sponsored by AMETEK Process Instruments. We are a worldwide manufacturer of process analyzers and instrumentation, and we serve a wide range of markets from environmental monitoring to hydrocarbon processing, as well as refining and petrochemicals, power generation and natural gas, to just mention a few. Our engineering and manufacturing activities take place across several facilities in North America, and we do serve the globe through a direct sales and service office, as well as many wide range of factory-trained representatives and distributors, as well as service technicians, so that we can provide responsive local service and support to all of our end users. So with that, Tim, I'll turn the presentation over to you.
Thank you, John. Well, good morning, good afternoon, good evening, from wherever you're calling from. Thank you for joining in today's call. Today's topic is going to be a little bit different than usual, but very much focused on safe combustion control and all the considerations that you would want to have around firing hydrogen in your burners. And so some of the things that we're going to cover in this presentation is really discussing this hydrogen as a fuel concept, and then what does it really take to make it a safe in combustion. So we'll talk about some of the trends that are going around globally to decarbonize existing assets, and some of the advantages hydrogen has in reducing the carbon footprint. We'll also talk about some of the properties of hydrogen versus methane, some of the physical properties that are of interest, and then some of the combustion properties that might be useful for consideration. We'll also talk about impact on retrofitting the existing equipment in the field. So based off of some of the literature review, some of the things to consider that may or may not be impacted when you retrofit existing assets. And then also some of the risks associated with hydrogen fuel. And finally, we'll conclude with some of the flue gas measurements for safe combustion control. Now, with that being said, let's start talking about decarbonization. So the movement towards decarbonization is happening globally, and as companies and countries and governments are evaluating their role in climate control and ways to reduce greenhouse gases, there's becoming an increasing focus on reducing carbon dioxide emissions. And still, even though there's a focus on reducing emissions, there are many industries that still require combustion for power and for heat generation. And that includes some of the hard to decarbonize industries such as steel, cement, and chemicals, as well as a number of the mobility vehicles out there, whether that be different types of transportation, from ships to air traffic to cars. And when you focus specifically on decarbonizing, carbon capture methods, there are really three different types of carbon capture methods available. The first one is post-combustion capture. So basically, if you see the reaction at the very bottom, this is a traditional combustion reaction using methane. One of the direct things that you can do in order to reduce your carbon footprint would be to simply just scrub out the CO2 after the combustion process. So that's one option. You can post-combustion capture by removing the CO2 after it's combusted and remove it from the flue gas. You can also consider some pre-combustion capture mechanisms. So one would be to change the fuel. Now you could change it to a low carbon fuel source, or you could change it to hydrogen, which is a zero carbon fuel source. As you might imagine, hydrogen only consists of hydrogen atoms. So the hydrogen molecule is a zero carbon fuel. That's one thing to consider, and that's a pre-combustion because it's before the combustion process. And then you can also considering oxy-firing, which is combusting with high purity oxygen, which basically means that by firing with high purity oxygen, you're really reducing the amount of inerts that you have to heat up. So removing any nitrogen from the air that would traditionally be there from ambient air. So as a third option, by reducing the amount of nitrogen present, by increasing the oxygen concentration, you have less inerts, which means you're heating less volume of air, which means you have a higher heat available for transfer, which would ultimately reduce your fuel consumption. So those are three different carbon capture techniques that are available for for decarbonization. And if we evaluate each one of these directly, there are some advantages and disadvantages, especially when you think about the installed base and existing assets. Now, when you look at post-combustion capture, removing carbon dioxide from flue gas, that's going to require carbon absorber towers to physically use, whether it's a mean-based solvent system or something like that, to physically separate out the carbon dioxide from the flue gas. And that's economical if you have it in a very centralized location. So if you're generating hydrogen fuel, for example, like it's in some type of autothermic or steam methane reforming circumstance, that would be one option that you can consider for post-combustion capture of that CO2 emission, because it's a centralized emission source. But if you have a number of fired heaters or dispersed emission sources, it could become very costly as you're trying to collect all of those different emission sources and pipe them together to a centralized emission source. So the economies of scale become more challenging when you look at small dispersed emission sources, such as like multiple fired heaters. So that's one challenge when it comes to post-combustion capture. And then if we look at oxy-firing at the very bottom, the use of high purity oxygen may have a little bit less equipment compared to post-combustion capture, but it's still more of a challenge because it's still punished by the economies of scale for sending that high purity oxygen and pumping it directly to the oxygen, directly to the burner. So when we look at the middle, the pre-combustion capture consideration for using hydrogen as a fuel, there's actually a lot more versatility from a big picture standpoint. So it's versatile where you can fire hydrogen in an individual burner or in a larger process. So it's more versatile for those larger centralized sources as well as for the small dispersed sources. Another advantage is that there's minimal impact on the combustion source itself. So you may have to make some modifications to the burner, but outside of that, there's still minimal impact to the actual burner on the ground, the actual equipment on the ground. And unlike oxy-firing and post-combustion capture, you don't have to think about the concerns of where do you put a carbon absorption tower for removing the post-combustion carbon. So that's one advantage where you don't have to consider additional plot space to relieve of the carbon capture. And then finally, it's a little bit more scalable when you think about it, because there's just going to be a fixed cost per unit. You're going to change one burner to fire hydrogen, change another burner to hydrogen. And so as opposed to having the concerns about consolidating all the emissions and sending it through a pipeline to a carbon absorption tower, you're instead thinking more about how do you retrofit different burners. And so there's more of a per unit cost as opposed to regardless of the size. So all of those things considered, hydrogen fuel certainly offers more versatility, especially when you start talking about small dispersed sources that might be around a chemical plant or a refinery. So that being said, now if we were to use hydrogen over natural gas, there are some things to consider. And so let's look at the physical properties of hydrogen versus methane. I think one of the important things to consider is that just by itself, hydrogen is a lot smaller compared to methane. It weighs a lot less. So it's 8 times less mass, it's 8 times lighter compared to methane. And as a result, it has a much lower density. And that density also gives it more molecular speed. So if you do some of the kinetic calculations, you'll see that hydrogen is 3 times faster. It'll disperse 3 times faster. It'll diffuse 3 times faster compared to methane. And then when you start to consider convective flows, hydrogen certainly has an advantage of molecular speed. And when you talk about flammability at a high level, hydrogen is much more flammable at a wider range of flammability limits and concentrations versus methane. So that's certainly something to consider, especially around flammability and safety. Now, if you look at it from the combustion standpoint, some of the combustion properties of hydrogen versus methane, I think one of the interesting things to point out is that hydrogen actually has a 3 times less of a heating value compared to methane. So in order to have the same heating value, the same heat release at the burner, you're going to need to flow in 3 times more hydrogen compared to methane. So that's just one of the kind of the practical considerations. Some other things to consider is that the flame speed of hydrogen is much faster compared to methane. Because those molecules are moving a lot faster, because it's lighter, it's less dense, those molecules move a lot faster, and that flame speed ultimately means that you're going to have a shorter flame. So even more reactive and even shorter flame. And some other things to consider is that with the hotter, is that hydrogen itself also burns hotter. So it has a higher adiabatic flame temperature compared to methane, which makes it more prone to NOx emissions, to higher NOx emissions. And then as far as autoignition temperature goes, these are roughly autoignition temperatures, but you can see that they're not too far off. So I think that the biggest thing to compare when you look at hydrogen versus methane autoignition temperature is that above 585 degrees C, above 575, some of the numbers vary a little bit, but above that temperature, both hydrogen and methane are very much privy to autoignition. So not too much of a change there. But some of the big reflection points are that hydrogen flames are 10 times faster, they burn hotter, but you're going to need more hydrogen pumped in order to have 3 times, in order to compensate for the heating value. Now, so what does that mean as far as the implications of firing? So above, on the very top of the slide, is the reaction mechanism for hydrogen fuel versus the traditional methane combustion reaction. And in order to get the same heat release, I multiplied it by 3 roughly. And one of the things that you notice is that the first thing is that you're going to have to, in order to have the same fired heater duties, you're going to have to increase your hydrogen volumetric flow rate by 3 times. So that's the first thing to kind of consider. Some other things to consider is that just based off of the comparison, hydrogen actually uses a little bit less methane, a little bit less air compared to methane. So that may mean that you operate at a slightly higher. If you share a burner with methane and natural gas and you switch between methane and natural gas, hydrogen will effectively use less natural gas or less air compared to methane. So if you're trying to work towards a ideal air to fuel ratio, if you're going to fire 100% hydrogen all the time, you may adjust the combustion air rate slightly. And then, as I mentioned before, there is a potential for higher NOx emissions. The faster molecular speed means that hydrogen is going to have a faster flame. That faster flame is shorter, reacts in a shorter zone, which creates more hotspots that produce NOx. And so we'll talk about NOx. Next. So for those of you who may not be aware, NOx is created from high excess oxygen and also high temperatures. So if you have poor mixing within the burner, within the flame, you create these little hot spots that directly impact the flame temperature. And these hot spots can trigger the production of greater NOx emissions, because NOx is generated from high temperatures and high oxygen concentrations. So some things to think about is that as you operate with hydrogen with a higher flame temperature, you're going to be more predisposed to NOx production. So some things to consider would be to use a low NOx burner, even though you may still need to monitor them. And as far as oxygen concentrations go, you should look for some type of ideal optimized combustion set point, because you don't want to operate too low where you're at a safety risk, but you also don't want to operate too high where you're predisposed to generating more NOx because of higher oxygen concentrations. So that's kind of the give and take when it comes to NOx production. Any questions so far, John?
Nope, none so far, Tim.
Okay. So some things to think about to reduce NOx is, as we move towards hydrogen burners and hydrogen as a fuel source, there's going to be a lot of discussion on burner design in order to compensate for the NOx production. And the objective of any type of low NOx burner is to reduce the peak flame temperatures, reduce those pockets within the flame envelope that are high temperatures. So there are three ways that burner manufacturers use in order to reduce the peak flame temperature. The first way is to stage the fuel. And by stage the fuel, it means instead of injecting all of the not all of the fuel directly to the nozzle, you could also, one mechanism would be to stage the fuel injection downstream of the burner throat. So have a larger burner throat, as you can kind of see here in this picture, and actually put additional holes to inject secondary and tertiary fuel, so that not all of the flame is seeing all of the fuel and all of the air at the same time. By staging the fuel, you're less prone to having everything ignite all at once, creating a hotspot. So by staging the fuel, you have more areas to continue that combustion reaction at a longer path length compared to a traditional raw gas burner, for example. Another alternative, or another way to reduce NOx emissions, would be to also stage the air. So some burner manufacturers are looking at ways to stage the combustion air by injecting that combustion air downstream at different points, so that when you inject the fuel, you burn some of it with the first injection of air, then you burn more of the fuel with the second injection of air, then you burn the fuel even more so as you inject air. And as you stage the air, it forces the flame to be a little bit longer, but also to have less hot spots because they're not all mixing at the same time. And then the last approach that burner manufacturers use to reduce NOx would be through some type of inerting process. And inerting can be done in two different ways. The first way is through recirculation of the actual flue gas. So as you can kind of see down here, this burner on the bottom right has this little recirculation path right at the nozzle. And that's based off the geometry of the burner, that's based off a lot of different parameters. But that little flue gas recirculation brings the process of combustion down, which is already inert, so it's basically going to be water vapor, brings it back into the water vapor and diatomic nitrogen, bring that back into the flame to cool the flame, because that relieves some of the potential for hotspots and overreaction of the fuel and the air mixture. So flue gas recirculation within the burner throat is another way to cool the flame by injecting that flue gas, by recirculating that flue gas locally to the burner. So that's one way that burner vendors are using. And then another way, which may be a little bit more expensive, would be to inject steam directly into the burner flame. That would be one way that you could very quickly inert and cool the flame, because water would be used as the inert, and then also to absorb that heat from the flame directly. So as you think about hydrogen burners and next generation hydrogen burners, these are some of the concepts that they're going to be using as they promote those new burner designs and think of ways to reduce NOx emissions for hydrogen. Okay, so we talked a lot about we talked a lot about hydrogen and how it compares to methane and how the burner considerations could be evolved to reduce NOx. So next, I want to share with you some research that I found that is very enlightening for actually implementing a transition from natural gas to a hydrogen type fuel. And so the source that I reference at the bottom is, you can reference that if you're interested for more information. But it was a joint effort between John Zink and Chevron, and that joint effort allowed them to explore what would it take to actually use hydrogen in an existing asset type scenario. So they did a combination of modeling and simulations and did a pretty thorough analysis. But some things that I'd like to take away and share with you are that from a burner standpoint, the burners operated without any modifications. So they went from natural gas to 90%, 95% of hydrogen fuel without any type of modifications on the burner. And given a traditional burner as it is, low NOx or raw gas or traditional, there were no operational difficulties or instabilities that were encountered during the testing process. So from an impact to the install base, a lot of burners as they are don't necessarily require any major modifications to start firing hydrogen. One thing to note is that the research in the study basically found that the reduced flame length caused a lot of the hotter metal parts near the burner, to become hotter. So at a higher concentration of hydrogen in the hydrogen flame length of about 95% of hydrogen, 100% hydrogen, the flame detector showed metal temperatures that were significantly higher than before. So from 480 degrees Fahrenheit to 1300 degrees Fahrenheit when firing 95% hydrogen. And that higher temperature was still within the acceptable range of the material for the 310 stainless steel flame detector, with no visual adverse side effects. But it does make you think that if you are going to move to a hydrogen fuel source, to consider increasing the metal thickness of those type of metal pieces at the burner, or upgrading the material depending on what you find in the field, because that hydrogen flame will be shorter, and it will certainly make the metal parts near the burner hotter. So something to think about there, especially when you start to adapt it to the install base. Now, other things. Now, also from that study, one of the things that they did was different types of modeling, and one of the things that they modeled was different heaters and reformers and steam generators. And one of the things that they noticed was that when you use a hydrogen flame, the radiant temperatures near the burner operate slightly hotter. So the radiant zone temperatures are slightly hotter. They're not astronomically hotter, but they are slightly hotter than before. One of the other things that was reported was that convective temperatures actually operate slightly cooler. So partly because of the reduced mass flow rate of the process of combustion, but also some of the properties of generating more water vapor compared to traditional combustion. So some observation there within the modeling. And then from a practical standpoint of the actual testing, NOx emissions at the burner were, from a ppm level, significantly higher. So something to think about is if your parameters are written to ppm levels of NOx, it may using hydrogen may have a significant effect on your emission limits. Now, that being said, when you look at it from a mass flow rate, using hydrogen on an ultra low NOx burner really doesn't change the NOx emissions very much. It actually slightly increases the NOx emissions, but not it was slightly increased with a low NOx burner. A low NOx burner actually reduced the emissions compared to a traditional burner, which is what it says in this case. So the mass flow rate with a low NOx burner generates less NOx compared to a traditional burner, but you're still going to have some type of increase in NOx emissions, whether that be through a mass flow rate or a ppm basis. So it would be significantly higher. Other things to point out is that when you think about the fuel system and the fuel train, that when they operated 100% hydrogen fuel, the pressure increased a few psi. It wasn't a major change, but it was certainly a change. The pressure increased in some cases from 17 psig of natural gas to 21.5% net of pure hydrogen. So there are some changes in pressure that you'll see as you move from natural gas to hydrogen. But when they did a preliminary evaluation of the metallurgy itself, the existing fuel gas showed that it was still adequate for hydrogen service. There wasn't anything that needed to be changed. No significant piping material modifications that were needed to go from refinery fuel gas to hydrogen. And I know a lot of refinery fuel gas right now has 10 to 40% hydrogen, depending on the case. But as you can see at the very bottom, the study really reported that there were no major showstoppers when using hydrogen as a fuel in these traditional assets. Now, those are some of the impacts on the actual install base, but when you think about it from a risk standpoint, there are a few things that I want to summarize and mention. Now, the first thing is that, although I didn't mention it earlier, premix burners have the most risk when it comes to flashback. It is very common for premix burners to have a very narrow window of operation. And because hydrogen has such a higher flame speed compared to methane or natural gas, hydrogen is much more privy to walking backwards and causing a flashback event. So if you have a premix burner on your facility, you would very much need to have that considered for, is it capable of handling hydrogen? Does it require a change of combustion air fuel rate? Does it require some change in pressure? Because there is a risk with premix burners in flashback. So something to consider there. Other risks associated with hydrogen firing include thermal NOx production. So hydrogen has a hotter flame temperature. It certainly does pose that risk for higher NOx emissions. On a mass flow rate, it's not as much of a concern, although it does increase NOx production. But the biggest concern and risk is if your permits are written towards ppm levels. So if they are ppm levels, there may be a penalty associated with changing from from natural gas to hydrogen, because from the reporting standpoint on a dry flue gas basis. So something to consider there, especially if you're uncertain whether or not your permits are written to ppm levels or mass flow rates. That's something to consider. Other risks associated with hydrogen firing would be to operate the radiant tube temperatures too hot. Now, that's not necessarily very likely. The studies that I went through did not show a very high increase in tube temperature with radiant tube temperature with hydrogen, but you have to be mindful of your firebox geometries. You don't want something to be too close that would be a concern. So something to monitor wouldn't necessarily be a likely concern, but something to keep in the back of your mind, especially if you're uncertain how your firebox geometry plays. Other things include risk of overheating metals around the burner, whether that be the flame rod or flame detectors. As I mentioned in that previous study, the metal parts exposed to the flame were still operating within the acceptable limits, but they were still operating significantly higher than a typical natural gas flame, if you will. So in order to mitigate that end users would want to consider upgrading the material or increasing the thickness of the metal itself to dissipate heat. And finally, the last risk that would be worth discussing is the risk of a flame out event. So it may not necessarily be likely that there could be a flame out event, or I should say an accumulation of a combustible vapor. Hydrogen does have a very high reactivity, it has a very high molecular speed. It's very likely that hydrogen will mix a lot better. Even in a poorly mixed firebox, it's likely that hydrogen could interact with neighboring flames to combust over time. But it is something to consider thinking about and looking at how to monitor that downstream with flue gas measurements. And so end users could install some type of flue gas monitoring system in order to monitor for excess oxygen or combustibles or percent levels of hydrogen. And then also end users could consider operating at a slightly higher oxygen concentration, just so that they're not at a point where they're going to operate too low excess oxygen and run the risk of creating a fuel-rich condition. Now, on that last point, let's talk about the flue gas measurements themselves. Now, when we look at traditional flue gas measurements for combustion, all combustion is going to have some type of oxygen, fuel, and heat combination, whether that be natural gas or hydrogen. And when we think about traditional firing with natural gas or with other types of fuels, generally what we see is some type of combustibles compounds. Combustibles, as we define it, are compounds that are part of the incomplete. Combustibles are compounds that indicate incomplete combustion. And in the case of reacting with methane, you would see carbon monoxide and or hydrogen present at the detector. And so that being said, our combustion, one thing to consider would be a combustibles measurement. So for firing natural gas, when you're firing with hydrogen, though, there are other things to consider. Specifically, looking at hydrogen-fired burners, you're still going to need an oxygen measurement because you're still going to have to monitor at excess oxygen levels. You could still monitor combustibles, specifically ppm levels of hydrogen, because ppm levels of hydrogen, although it may be unlikely because of mixing, it still would be worth monitoring for that assurance. And then, especially if there was some type of tube leak that would start to produce carbon dioxide or carbon monoxide and hydrogen. And then from a hydrocarbon standpoint, you could have a hydrocarbons or methane detector that could be used for percent level measurements of hydrogen during flame out or during some type of process tube leak. And then finally, some other relevant combustion measurements would be measuring the sample itself to make sure that you have an accurate representation of the process. So combustion analyzers that use zirconium oxide can measure net oxygen measurement. Combustion analyzers that have catalytic detectors can actually measure ppm levels of combustibles, which includes ppm levels of hydrogen. So if you have a flue gas analyzer that has a catalytic detector, that catalytic detector can not only measure carbon monoxide, but it could also measure hydrogen as it was indicated before. And then finally, with flue gas analyzers that may have a catalytic detector for measuring percent levels of methane or hydrocarbons, that percent level methane measurement or percent level detector can actually be used to monitor for percent levels of hydrogen in the flue gas, or to measure some type of process tube leak that may be producing carbon monoxide. So something to think about when you have combustion measurements and flue gas analyzers. So, as from this presentation, the use of hydrogen as a fuel has much more versatility for small dispersed emission sources compared to for plants that have those small dispersed emission sources that may have multiple heaters or multiple zones. Some other things to take away are hydrogen as a compound is lighter, it moves very quickly, it's more flammable compared to methane, and it gives a hotter, smaller flame. And that hotter, smaller flame generates significantly more, has a risk of creating more NOx. Some other things to take away are that hydrogen fuel needs to flow at 3 times faster compared to natural gas in order to meet the same heat release. So just something to consider as far as a heat release standpoint is concerned, designing your heater and sizing those lines for hydrogen so that they can handle that extra flow of hydrogen. Some other things to consider is that premixed burners are, again, they pose a risk of flashback over raw gas burners. And finally, as mentioned on the study, existing equipment does not appear to have any major modification need to fire 100% hydrogen, although there would be things that you want to consider as you transition from natural gas to hydrogen. And that includes, exposed metal at the burner, your NOx permit, and if you have a premix burner or not. And if I could add one more thing as takeaways, is that flue gas analyzers that use catalytic detectors that use zirconium oxide can still be used in these types of application to monitor for ppm levels of combustibles, whether that just be hydrogen or percent levels of hydrogen and hydrocarbons during operation. Now with that, I ask if there's any questions, feel free to raise your hand or submit your question in the chat.
Hey, Tim, thanks for that. There've been some discussion and some questions along the way in the chat box. So maybe start back. There was a number of questions around slide number 10, around basically how to handle hydrogen safely in the combustion process, and the discussion around staging fuel and air and how complicated that might be for burner control. So I just wonder maybe if you could speak on that for a minute.
Thanks, John. So the staging of fuel and air is largely the role of the burner manufacturer. Burner manufacturers have that experience and that, in some cases, that computation of fluid dynamics to actually monitor and measure how to stage the air and fuel correctly. So that's not something that would be typical of an end user. That would be something that a burner manufacturer will want to develop and propose in a burner design. So that's where that role comes in, is burner manufacturers would be the ones that work towards meeting the spec through staging fuel, staging air, or inerting in some fashion. It'd be a little bit more complicated to talk through the actual details of including that into the heater design, and I'm not really sure if the heater design would be privy to that as well, especially if it's existing assets. So I would certainly leave that to the burner manufacturer. Does that answer the question, John?
Yep. Okay, that's good, Tim. On slide 11, there was a couple of questions. Maybe one is just a clarification. On slide 11, I think you mentioned 95% hydrogen fuel, and the question was, what is the background 5% in the 95% hydrogen fuel?
It's natural gas and methane in some combination. I think it's like, I'd have to go check the study again, but I think it was like 4% natural gas and 1% nitrogen, something like that. Okay.
And then another couple questions, perhaps related directly to study, but also just maybe more broadly. One is, can the hydrogen and air be preheated to improve efficiency?
Yeah, I would recommend preheating the air, because so preheating is an interesting thing. Preheating can certainly increase efficiency, absolutely. The only thing about preheating is that preheating also means that you're going to preheat air that's sent to the flame, and that you're actually going to have a hotter flame temperature as a result. So that may be at the expense of your NOx emissions. But that being said, it is very common for for burner manufacturers and furnace manufacturers to preheat air to increase efficiency. So that the answer is yes, it would increase efficiency. The other part is it could increase NOx emissions because you're actually making the flame hotter by adding heat to that.
Okay, and another question that was sort of in these two slides was, is the flame temperature the measured variable to control the different injection flow rates using the staging techniques?
It's certainly, so flame temperature is the biggest determination of, I mean, that's one of the two determinations. Oxygen concentration is the other one. So burner flame temperature is certainly something that's critical for NOx production. I think it's a combination of, I'm not sure how you would actually measure that unless you had something that was monitoring for hot pockets in the flame, and even then, with that thermal imaging, I'm not sure how meaningful it would be. I think from a burner design standpoint, it really comes down to testing in some cases, but in simulation in other cases. But I think the biggest thing that would be monitored is when's the right location to re-inject where's the right geometry to re-inject the fuel into the flame, or where's the right place to re-inject the air into the flame. But it's a combination of flame temperature. As I said, I'm not sure how you would monitor that specifically, but you would also have to consider the oxygen concentration, because that would certainly play a role in it. And if there's anything that you can do with the geometry to guarantee recirculation, that would certainly play a role in reducing NOx emissions as well.
Okay, and I think you may have addressed this during your talk on this slide, but around the higher temperatures. But there was a question on, do the higher temperatures mean the metallurgy has to be revisited? I recall you maybe discussing, maybe you could just expound on that a little bit.
Well, I don't want to generalize. I just want to kind of state the facts that were kind of proposed from the study. But one of the things that was observed was that the metal flame detector, the 310 stainless steel flame detector that was used in this case, that went from 480 degrees Fahrenheit with natural gas to 1300 degrees Fahrenheit using 95% hydrogen. And so it would be wise to look at what metal parts are exposed to the flame, and also consider also observe it. Is it deteriorating faster over time? Is it glowing hotter than it usually is? Those would be some indications that you would either want to change the material or increase the thickness to dissipate that heat. So it's more of a design of the burners that you currently have in the field, but it's also something to look for. It's certainly something to look for. But it's certainly application specific.
Okay, and there was a couple of questions as you got into slides 13 and 14. This first one probably applies to the whole presentation, but presumably running hydrogen fuel, the question is, could that change the hazardous area classification to include Group B?
That's a great question. I am uncertain of that answer, but that is a very great question to talk with certification bodies. Absolutely.
Okay. And then I know on slide 14, as you were this slide and the next slide, you were talking about the risks. And one of the questions was, are the risks being evaluated to remove those risks, or are they always an issue and it's more about mitigating the risks?
Could you repeat that one more time, John? I'm just trying to.
The question was, are the risks being evaluated to remove them, or will they always be an issue? And I took that to mean, mitigating the risk to some lower, risk threshold, but the risk is still present.
Let's go one at a time, real briefly. For premix burners, I think that's always a risk. So that's something that you would have to make sure that the premix burner can handle the hydrogen, and make sure that it's not going to flash back with any major fluctuations in either fuel composition or turn down of firing rate. So that one would always be an issue. I mean, the thermal NOx would certainly be an issue if you're going to operate at the same heat release. So that would certainly be those first two would be ones that you have to like investigate to mitigate. For the radiant tubes, it may not be an issue. As I said, it wasn't a significant increase. It was only a few degrees, like 10 or so degrees hotter than the previous ones from the examples in the study. But that's probably nothing to mitigate there. It's just an observation, just to check as you go from natural gas to hydrogen. Other risks of overheating. I mean, that's mitigating if there is any risk at all. So mitigating the risk through larger metal thicknesses or through upgrading material. So that's something to mitigate. And then as far as the risk of combustible vapor, as much as it's hard to consider, you know, flame out is certainly a concern of mine, and certainly a concern when you think about firing with hydrogen. And I've had a lot of conversations with our PhD VP of technology to talk about how would this actually play out. And certainly hydrogen is a much faster molecule, move a lot faster, it'll disperse a lot more, even without the convective forces. So it's 3 times faster than natural gas. So it's faster, it's also more reactive than natural gas. It may react with any available excess oxygen at the burner level and the flame level. So that'll be shown at a lower oxygen concentration. But that would certainly be one thing to monitor and to mitigate, just to make sure that you either have some type of flue gas analyzer downstream to make sure that you're operating at the correct oxygen and ppm level of hydrogen, ppm or percent level of hydrogen levels. If ideally they would be very low, if not zero, but that's something to consider. And then as far as mitigating it through a safety margin, I think it would be important to think about what's the safety margin that we're willing to take for a higher oxygen concentration. What's the higher oxygen concentration we could use to mitigate any type of fuel-rich condition? So I hope that answers your question, John. But those are some things that there are certainly all ongoing concerns that should have some type of mitigation path as I kind of go through that.
Okay, this one, there's actually a little bit of commentary in the chat as well, but just around facilities starting to use hydrogen on any kind of scale, and there was some discussion within the chat that on refineries, you know, wanting to operate at varying percentages of hydrogen in the fuel gas, and then the challenges that presents in terms of controllability and flame stability as the molecular weight varies. I just didn't know, Tim, if you wanted to speak maybe on your experience or your perception of sort of the use of hydrogen within facilities and how that, you know, what have you seen so far?
Well, a lot of refineries right now are using refinery fuel gas, and refinery fuel gas can have anywhere between 10% hydrogen to 40% hydrogen to 70% hydrogen. I think the biggest challenge is when your fuel gas changes in composition significantly. Like if you're going to vary from 10% hydrogen with 90% natural gas and go from that to 70% hydrogen, that poses a major change to your flame speeds. So that would present a big concern for flashback events. And some of the literature that I went through mentioned that, you know, premix burners have shown a lot of can certainly show flashback events, and that can certainly happen like outside of the 10% to 40% refinery fuel gas window of 10 to 40% hydrogen in refinery fuel gas. So like end users are using hydrogen right now, especially in refineries. But as you start to look at risks, there is a risk, I would say, as well, of using varying fuel compositions without many modifications to the burner setup or air level, because generally around premix burners, but you still want to be careful of flashback events, flame speeds that aren't accounted for, especially as you go into higher percent hydrogen levels. So there would certainly be a risk if you're going to change composition often.
Okay, and maybe just one last question, Tim. Just on the study, if you know the John Zink and Chevron study that you mentioned, do you know if they used pure oxygen in their tests at all with hydrogen?
No, it was just air. It was
Just air. Okay.
Yeah.
All right. No, that's good. There are a couple other in there, Tim. I think we'll take offline with email response to a couple of folks on a couple of more specific questions that they had. I don't know, Tim, if you have any closing comments that you want to make.
Well, I guess my only closing comment would be that although there are certainly risks of firing hydrogen, I think they're still able to be mitigated. And I think the biggest encouragement is that all the literature seemed to indicate that there was no major need for any modifications to existing equipment. So fuel train systems can still be used as they are. Same with some of the existing burners. There will be things to think about, especially with, the flame rods, and same with the NOx permits and stuff like that. But it's not, I wouldn't say it's outside of the control that I was even under the impression of before. So I hope this presentation provided some encouragement that as end users start looking at 100% hydrogen as a fuel gas, as a fuel source, that it doesn't require as much to change and convert from natural gas to hydrogen from a existing installed base, from an existing burner and furnace and fuel train setup. Other than that, if anybody else has any questions or comments, feel free to reach out to me at tim.talent@ametek.com. And thank you for your time.
Yep, I do, Tim. Thank you again for sharing your expertise today, and I thank everyone on the call for their time in attending today. Hope you found the session informative and interesting. I have posted several useful links there on the chat on the products and also how to reach local contacts related to today's presentation. And as I mentioned, we did record the session, and we'll be posting that on our AMETEK Process Instruments YouTube page in the coming days. So again, thank you for your time and enjoy the remainder of your day.